So these are going to be the things that we're going to have to know. This is going to be our repressor protein gene, LAC1 repressor protein gene. That's going to be our lactose inducer, promoter, operator, and then these are going to be our structural genes. And then from the promoter all the way to the structural genes, that's the whole thing is going to be the example that we're going to use is going to be the E. coli lac operon. And then this is going to be our RNA polymerase, and then our LAC1 repressor, which is the same thing as this. So it depends if there's an inducer bound to it or the repressor bound to the operator. So in the first one is going to be RNA polymerase, which is this one, binds to the promoter. And then if it binds to the promoter, and then it's going to be able to transcribe to the CYA structural genes until it hits a stop codon and then it falls off. The other example is if the LAC repressor, which is this one, binds to the operator, that's going to create a roadblock. So if the LAC1 repressor binds to the operator, it's going to create a roadblock and there's going to be no transcription. So that RNA polymerase cannot continue to go this way. If there is no lactose, so for example that one, that's going to be our lactose, which is our inducer, the LAC repressor will bind to the operator, which is going to be this example right here. So if there's no lactose, then the repressor will bind to the operator because you don't want transcription to occur. So it's going to create that roadblock so that RNA polymerase cannot go this way. If lactose is available, however, then the lactose, which is the inducer, will bind to the LAC1 repressor protein so that it can't bind to the operator. So then if that one binds, the lactose inducer binds to the repressor, it will change the shape of the repressor, so then the repressor can no longer bind to the operator, and then there is going to be transcription. There are a few cases when we're going to call it a leaky expression. This is when there is no lactose. So there's no lactose there, but there's still a little bit of transcription happening. So a couple examples that we're going to use is going to be like, let's say the promoter. This is the promoter. If the promoter cannot bind, then there's going to be no transcription. These are all for mutants. So let's say the promoter is a mutant promoter, it doesn't work, then RNA polymerase cannot bind, then there's going to be no transcription. It cannot go that way because RNA polymer has to be bound to the promoter. The second example is if the LAC repressor protein gene cannot bind to DNA, there is going to be no roadblock. So it's this one right here. So if the LAC repressor gene cannot bind to the DNA, there's going to be no roadblock. So there's going to be transcription. No roadblock means it's going to allow RNA polymerase to continue to keep going, and there's going to be transcription. The third example, if the LAC repressor protein gene cannot bind to the inducer. So let's say that one, it's defective, it can't get, it's not working. It cannot bind to the inducer, which in this case is lactose. There's going to be no transcription because the repressor is bound to the operator. So at this point, if that one cannot bind to that one, that means because the repressor cannot bind to lactose, it's bound to the operator, so there's going to be transcription. There's going to be a roadblock. So there's going to be no transcription because the repressor is bound to the operator. And then our fourth example of, let's say there's going to be a mutant operator. So the operator is not working. It cannot bind to the LAC repressor protein. There's going to be no roadblock. So obviously there's going to be no transcription. So for our application, we're going to use inducible diphtheria toxin, Operon. And so remember that Operon, it's going to be a promoter, an operator, and the structural genes. But the example for this one is going to be on the diphtheria toxin. So we're going to have our repressor gene, which is diphtheria toxin. And then we're going to have the promoter. We're going to have an operator. And then our gene, like I said, is going to be our diphtheria toxic gene. So the first thing that's going to happen, if in the environment there is iron available, there's usually a lot of iron available, which is this little triangle, it would bind, the iron will bind and then activate the repressor. And then if it binds and activates the repressor will bind to the operator and it will block transcription. So let's go over here, because then the repressor will bind to the operator. So if there's like a little repressor right here, it would bind to the operator and then it will block transcription from happening. So if there's a lot of iron, it binds to the repressor, and then like I said, the repressor will bind to the operator, and then there's no transcription. The example for human throat, however, this is the second example. If there is low iron, for example, it's bound to the proteins transferrin or lactoferrin, which are natural defenses, then if there is low iron or no iron, then it's inactive. It cannot bind to the operator. So the iron, like I said, would be the repressor right here. Well, I don't know if iron is going to be the repressor, but then the repressor, it's going to bind to the operator. I take that one back. The repressor cannot bind to the operator. So if there's low iron, we will turn on the diphtheria toxin Operon, and then it's going to continue to go, because like I said, that one cannot bind to the operator, so there's going to be transcription, and the diphtheria toxic gene will transcribe into RNA, and then the RNA will transcribe into diphtheria toxin, and then which is absorbed into the blood, which will cause heart damage, a pseudomembrane, which is kind of large in the throat, and then it will also block airflow, and we can't rip it off because you can cause hemorrhage or heart damage. For the pseudomembrane, it's an inflammatory membrane. We worry because, like I said, it's big and it's going to create a block of airflow.